The universe is vast and seemingly infinite, but there is a limit to what humanity can observe. This boundary marks the farthest reach of light from the most distant galaxies, arriving at our eyes after a journey spanning billions of years. This horizon is not merely a distance boundary, but also a window into the universe's past. The cosmic boundary is not a fixed physical edge like a coastline or mountain range. Instead, it is an abstract concept reflecting the farthest distance light, and therefore information can travel to reach Earth since the universe began with the Big Bang. This idea not only shapes how we perceive the universe, but also raises profound questions about the nature of space and time. The concept of the observable universe, or the cosmic boundary, encompasses the range of the universe visible to us through light or electromagnetic radiation from distant objects. Interestingly, the light from stars and galaxies billions of light years away takes just as long to reach Earth, meaning what we observe today are vintage images of the universe from the past. This makes the cosmic boundary not just a spatial limit, but a natural time machine, allowing us to reverse the course of history and explore how the universe evolved from its earliest moments. The maximum distance observable by humanity is currently estimated at approximately 46.5 billion light-years from Earth. This figure may seem contradictory, as the universe's age is about 13.8 billion years. However, this discrepancy is explained by the expansion of space, a phenomenon described by Einstein's theory of general relativity. Even though the light from distant objects began its journey billions of years ago, the space between those objects and us has expanded during that time, pushing them farther away than their original positions. This means that the cosmic boundary is not a fixed limit, but continuously extends as the universe expands. However, what lies beyond this boundary remains a significant mystery, regions where light or any radiation has yet to reach us, rendering them entirely beyond the reach of direct observation. The importance of the cosmic boundary lies not only in the immense scale it represents, but also in what it reveals about the universe's nature. Identifying this boundary helps scientists better understand the scale, structure, and history of the universe. It is a realm where current physical models, such as general relativity and the Big Bang theory, are tested and validated. Observations at the cosmic boundary provide clues about the universe's earliest stages, from its initial expansion to the formation of galaxies, stars, and other large-scale structures. This boundary also prompts profound cosmological questions. Is there anything beyond the observable universe? And if so, does it resemble what we see? The cosmic boundary is not just a measure of distance. It is also a symbol of humanity's relentless pursuit of the unknown. Every step in expanding our understanding of this boundary, through missions like the James Webb Space Telescope or future projects such as giant ground-based telescopes, not only illuminates the universe's history, but also inspires hope and curiosity about overcoming seemingly insurmountable limits. By studying the cosmic boundary, we gain insights not only into what happened billions of years ago, but also into humanity's place within the grand cosmic panorama. When we look toward the cosmic boundary, what we observe is not just the most distant objects, but a doorway to the distant past of the universe, a journey back in time spanning billions of years. Through the light from celestial bodies at the edge of the observable universe, we gain insights into not only what exists at the farthest reaches, but also how the universe formed and developed from its earliest days. Light and time are fundamental to exploring the cosmic boundary. Light, traveling at approximately 300,000 kilometers per second, is the fastest information carrier in the universe. Yet even at this speed, it takes billions of years to traverse the distance from distant celestial bodies to Earth. This means that when we observe a galaxy billions of light years away, we are actually seeing it as it was billions of years ago, not as it exists today. Light becomes the universe's newsletter, carrying messages from the past and recording the stages of the universe's evolution from the moments following the Big Bang. Through this, we can explore primitive galaxies, primordial gas clouds, and even the first stars, population 3 stars, formed from basic elements like hydrogen and helium. The clearest depiction of the past emerges when observing celestial bodies at the edge of the observable universe. These objects, often young and small galaxies, hold invaluable clues about how large-scale structures in the universe formed. Images of these early galaxies reveal how the first stars coalesced from primordial gas and dust, while allowing us to understand how galaxies merged, grew, and evolved over time. For example, with advanced telescopes like James Webb, we can observe regions previously confined to theory, providing empirical evidence to support current cosmological models. These images not only clarify the universe's earliest stages, but also help us understand how galaxies and galaxy clusters were formed, laying the foundation for the cosmic structure we see today. However, limitations in observation pose a challenge when studying the cosmic boundary. Because light takes an enormous amount of time to reach Earth, some objects we observe may have already transformed or no longer exist. A galaxy we see as a youthful, star-forming structure might have merged with another galaxy or been destroyed by powerful gravitational forces. The cosmic boundary thus resembles a snapshot of the past, where events have occurred, but their traces continue to propagate through space as light and electromagnetic radiation. This phenomenon is both awe-inspiring and a reminder of the limits of direct observation in modern cosmology. The ability to see the past through light is one of the cosmic boundary's most unique and remarkable features. It offers us a rare opportunity to study how the universe formed and evolved over billions of years. From understanding how early galaxies emerged to exploring the structure of the first stars and the distribution of matter, light from the cosmic boundary serves as a living timeline that helps humanity decode the biggest questions about the origin and evolution of everything in the universe. Each beam of light from that boundary is a piece of the universe's story, recounting its earliest chapters in a way no other medium can replicate. By studying this light frontier, we not only expand our understanding of the cosmos, but also recognize humanity's unique role in the grand narrative of the universe. The phenomenon of redshift in light is one of the most critical factors in understanding the cosmic boundary and the continuous expansion of space. It not only signifies the increasing distances between objects in the universe, but also serves as a key to decoding the universe's evolutionary processes since the Big Bang. Redshift and cosmic expansion are closely linked, reflecting the interaction between light and the expanding space. As the universe expands, light emitted from distant objects stretches, shifting from shorter wavelengths in the visible spectrum to longer wavelengths, such as infrared or even microwaves. This is analogous to how the frequency of a train whistle decreases as the train moves away, a phenomenon known as the Doppler effect. In cosmology, redshift not only provides information about the distance of distant objects, but also allows scientists to measure the universe's rate of expansion. The farther the objects, the greater the redshift, a relationship described by Hubble's law, which demonstrates the universe's continuous expansion over time. Light from the universe's early epochs provides the strongest evidence for redshift and the constant expansion of space. A prominent example is the cosmic microwave background, CMB, radiation. The remnant light from the Big Bang emitted approximately 380,000 years after the universe's birth. At that time, this light existed at visible wavelengths, but over billions of years of expansion, it has stretched into microwave wavelengths detectable today. The CMB is a fossil record of the early universe, offering invaluable information about the density, temperature, and structure of the universe during its infancy. The James Webb Space Telescope, JWST, along with other instruments like the Planck telescope, has used CMB data to reconstruct maps of temperature and matter distribution in the universe's earliest stages. The cosmological significance of redshift cannot be overstated. It is not just a physical phenomenon, but a critical tool for validating cosmological theories. Redshift plays a crucial role in confirming the existence of dark energy, a mysterious component making up about 68% of the universe's total energy. Dark energy is thought to drive the accelerated expansion of space, causing distant objects to move further out of our observational reach at increasing speeds. By measuring the redshift of light from distant supernovae, scientists first discovered that the universe is not only expanding, but doing so at an accelerating pace, a finding that profoundly altered our understanding of the universe's dynamics. Redshift not only demonstrates the continuous expansion of space, but also acts as a magnifying glass, allowing us to peer into the universe's distant past. It is an indispensable tool for measuring cosmic distances, exploring galaxy evolution, and testing theories about large-scale structures. Each instance of light stretching serves as vivid evidence of space's expansion, bringing us closer to unraveling the universe's greatest mysteries, from the first galaxy formations to the forces driving today's accelerated expansion. Thus, redshift is not merely a natural phenomenon, but a gateway to the deepest insights about the cosmic boundary. Imagine a light signal that has existed since the universe was only a few 100,000 years old. This is not science fiction, but the cosmic microwave background, CMB, the oldest remnant of light from the universe's early days. This signal not only persists, but also holds crucial secrets about the origins and evolution of the cosmos. The cosmic microwave background, CMB, is not just the oldest trace of light in the universe, but also a vivid testament to the earliest moments of time, helping us understand the universe's origins and its evolutionary journey. Regarded as a record of light from the dawn of time, the CMB carries invaluable information about the universe's history following the Big Bang. The light from the early universe is the source of the CMB. Around 380,000 years after the Big Bang, the universe underwent a significant transition. Before this point, it was too hot and dense, with free protons and electrons continuously interacting with photons, creating a sea of trapped light. Light could not travel far, as it was constantly absorbed and re-emitted by particles, making the universe opaque and unobservable. As temperatures dropped to about 3,000 Kelvin, the universe cooled enough for protons and electrons to combine and form hydrogen atoms. This pivotal moment, known as the recombination epoch, marked the first time light could escape and move freely through space. That light is the cosmic microwave background we observe today, a snapshot of the universe as it began its journey toward maturity. The transformation of light over time is clear evidence of the universe's continuous expansion. When emitted, the CMB was in the visible light spectrum and had a temperature of around 3,000 Kelvin. Over billions of years, the universe's expansion has stretched the wavelengths of this light, shifting it into the microwave region of the electromagnetic spectrum. Today, the CMB has a temperature of only about 2.7 Kelvin, just above absolute zero, corresponding to faint microwave wavelengths detectable only by advanced technology. Although it has cooled, the CMB retains its original structure, carrying information about the universe's earliest stages as a fossilized light relic from the primordial era. The cosmological significance of the CMB cannot be overstated. It is one of the strongest pieces of evidence supporting the Big Bang theory, which describes the formation and evolution of the universe from an initial hot and dense state. Observations of the CMB, particularly from missions such as COBE, WMAP, and more recently, Planck, have confirmed that the universe underwent a hot and dense phase before expanding and cooling to form large structures like galaxies, galaxy clusters, and superclusters. The CMB is not just an ancient artifact, but a cornerstone for testing cosmological models. Small temperature and density fluctuations in the CMB, known as primordial oscillations, reflect initial irregularities in matter distribution, which eventually led to the formation of the large-scale structures we observe today. Beyond affirming the Big Bang theory, the CMB serves as a powerful tool for investigating more complex aspects of the universe, such as dark matter and dark energy. Subtle variations in the CMB provide clues about the distribution of dark matter, while models of spatial expansion based on CMB data help us understand how dark energy drives the universe's accelerated expansion. The cosmic microwave background is not merely a trace of light from the early universe, but a treasure trove of information that reveals the cosmos's origins and evolution. From the light emitted in the universe's first moments to its journey through space and time, the CMB has become a golden key, unlocking the greatest mysteries of the universe's nature. With every advancement in observational and analytical technology, the CMB continues to offer new discoveries, solidifying its role as one of the most critical markers in humanity's exploration of the cosmos. The cosmic microwave background, CMB, is not only the oldest light still in existence, but also a trove of data helping us understand how the universe formed and evolved. It carries thermal imprints from the early universe, recording key events and processes that shaped the vast structures we observe today. Thermal imprints from the Big Bang are preserved in the CMB as tiny temperature fluctuations, often referred to as anisotropies. These fluctuations, differing by just a few millionths of a Kelvin, reflect minute variations in the density of matter in the early universe. Regions of higher density in the CMB are the seeds for the formation of galaxies, galaxy clusters, and superclusters. Conversely, lower density areas became the vast cosmic voids we observe today. The anisotropies in the CMB are not just ordinary thermal imprints. They are direct evidence that the universe was not entirely uniform from the very beginning. The seeds of cosmic structure are among the most important pieces of information provided by the CMB. From these slight density variations, gravity began to take effect, pulling matter together and gradually forming the large-scale structures we see today. Under gravity's influence, denser regions continued to attract more matter, evolving into galaxies and galaxy clusters, while less dense regions expanded to form the cosmic web. This web, with filaments of galaxies linked by gravitational forces, is the largest structure in the universe, and a direct outcome of the minor density variations recorded in the CMB. This helps scientists better understand how matter from the early universe evolved into the diverse and complex cosmos we observe today. Information about the universe's composition is also encoded in the CMB, offering deep insights into its nature. Detailed analyses of the CMB reveal that the universe is composed of approximately 5% ordinary matter, the elements and compounds that make up stars, planets, and all visible objects. Additionally, about 27% of the universe is dark matter, an invisible form of matter that plays a critical role in gravitationally binding galaxies and galaxy clusters. The largest portion, around 68%, is dark energy, a mysterious force driving the accelerated expansion of the universe. These figures not only define our current understanding of the universe, but also serve as the basis for predicting how it will continue to evolve over billions of years. The CMB is a thermal map of the early universe, offering a comprehensive view of its first stages of history. It records the earliest traces of inhomogeneity, which led to the formation of galaxies and other large-scale structures. The CMB not only validates key theories such as the Big Bang, but also provides a profound understanding of the factors shaping the universe's evolution, from dark matter to dark energy. Thanks to observational missions like COBE, WMAP, and Planck, scientists can now analyze the CMB with unprecedented precision, yielding new insights and guiding future research. Far from being just ancient light, the CMB is a rich repository of information about the universe's formation and development. From tiny temperature fluctuations to fundamental revelations about the universe's composition, the CMB continues to serve as a powerful tool for humanity to decode the history of the cosmos and unravel its greatest mysteries. To unlock the secrets contained within the cosmic microwave background, CMB, scientists have developed a range of advanced tools and technologies, each contributing crucial insights into the universe's origins and structure. These tools not only measure the precise fluctuations in the CMB, but also pave the way for revolutionary scientific discoveries. The telescopes COBE, WMAP, and Planck are three pioneering projects that laid the groundwork for studying the CMB in modern cosmology. Launched in 1989, the Cosmic Background Explorer, COBE, was the first telescope to detect and measure the CMB with remarkable accuracy. COBE not only confirmed the CMB's existence, but also revealed that, despite its apparent uniformity, the CMB contains tiny temperature fluctuations, evidence of early density variations in matter. These discoveries strongly validated the Big Bang theory and inspired further research. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, operational from 2001 to 2010, provided even more detailed data on temperature and density fluctuations in the CMB. WMAP determined that the universe is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, while also precisely estimating the universe's age at 13.77 billion years. The greatest leap in mapping the CMB in detail came from the Planck telescope, a project by the European Space Agency, ESA, which operated from 2009 to 2013. Planck not only created the most accurate map of the CMB ever made, but also measured temperature fluctuations down to a few millionths of a Kelvin. This data not only confirmed the universe's age as 13.8 billion years, but also provided critical information about its expansion rate, the Hubble constant, and composition. Thanks to Planck, scientists could delve deeper into how large structures like galaxies and galaxy clusters formed from the tiny density fluctuations in the CMB. Additionally, Planck's CMB map remains a valuable resource for testing cosmological models and exploring the universe's earliest stages. Future technologies and projects aim to elevate CMB research to new heights. One promising avenue of study is the search for primordial gravitational waves, signals of intense space-time oscillations shortly after the Big Bang. If detected, these signals would not only illuminate the universe's earliest phases, but also provide direct evidence for quantum physics theories and general relativity. Projects like CMB-S4, Cosmic Microwave Background Stage 4, and successors to the Planck telescope will significantly enhance the precision of temperature and polarization measurements in the CMB, offering fresh insights into dark energy, dark matter, and fundamental particles. Modern observational tools have transformed the CMB into a rich source of scientific data and a window into the universe's distant past. From COBE, WMAP, and Planck to future endeavors, each technological advance brings crucial discoveries, drawing us closer to unraveling the greatest mysteries of the universe's origin and evolution. Once a faint trace of light from the early universe, the CMB has become an indispensable tool, continually expanding our understanding of the vast cosmos. Did you know that the universe we live in is constantly expanding, causing the distances between galaxies to grow increasingly vast? This phenomenon not only reshapes our understanding of the cosmos, but also raises profound questions about its future. Let's delve into this extraordinary process and the far-reaching implications it brings. The universe's expansion began immediately after the Big Bang 13.8 billion years ago, marking a miraculous journey of ever-expanding space and time. From a starting point smaller than an atom, the universe has grown into an immense expanse that we can only faintly imagine, carrying crucial traces of the formation and evolution of everything that exists. The phenomenon of redshift is one of the most significant pieces of evidence affirming the universe's expansion. This phenomenon was discovered by astronomer Edwin Hubble in the 1920s, when he observed that light from distant galaxies was stretched, shifting toward the red end of the spectrum. This not only confirmed that galaxies are moving away from us, but also demonstrated that the entire universe is expanding. Hubble found that the redshift's magnitude is proportional to a galaxy's distance, leading to his famous law, Hubble's law. This breakthrough revolutionized science, debunking the old notion of a static, unchanging universe and ushering in a new era of modern cosmology. The essence of expansion lies in the space between galaxies stretching, rather than galaxies flying apart in a static void. This means that all distances in the universe, whether large or small, increase as space expands. Galaxies, galaxy clusters, and superclusters, large structures bound by gravity, do not themselves move apart, but the space between them elongates. This concept, though challenging to grasp, is key to understanding how the universe operates. This expansion has shaped the universe's structure, from the cosmic web of galaxies to vast voids. Astounding figures illustrate the universe's incredible expansion. Scientists estimate that the universe is expanding at a rate of about 70 kilometers per second per megaparsec, a distance equivalent to 3.26 million light-years. This means two galaxies 1 megaparsec apart move away from each other at 70 kilometers per second, while two galaxies separated by 10 megaparsecs recede at 700 kilometers per second. This accelerating speed not only helps define the universe's scale, but also serves as the foundation for measuring critical factors like the Hubble constant and dark energy, the mysterious force believed to drive the accelerating expansion of the universe. The continuous expansion of the universe brings new mysteries. One of the biggest questions scientists strive to answer is whether this expansion will persist indefinitely or eventually slow down and stop. Some theories propose that the universe will keep expanding until all objects are so far apart that they can no longer interact, leading to a cold and quiet end known as the heat death. Other models suggest that the universe might reverse its expansion, collapsing back into a dense state called the Big Crunch. Regardless of which scenario unfolds, the current expansion of the universe is crucial for predicting its future. The universe's expansion is not just a physical phenomenon, but a story of time, space, and evolution. From the faint light of distant galaxies to vast voids stretching billions of light-years, This expansion is the driving force shaping the cosmos we inhabit. Every advance in studying cosmic expansion brings new insights and moves humanity closer to answering the profound questions about the universe's nature. Dark energy is one of the universe's deepest mysteries, considered the key to understanding why the universe is not only expanding, but doing so at an accelerating rate. Although it has yet to be directly observed, dark energy has fundamentally altered how we perceive the universe and the forces that shape it. Discovered in the late 1990s, dark energy is thought to account for 68% of the universe's total energy. This revelation came from observing Type Ia supernovae, standard candles in the cosmos, which showed that distant galaxies are moving away faster than expected. This led to the conclusion that instead of slowing down due to gravity, the universe's expansion is actually accelerating. Dark energy, an invisible and enigmatic force, appears to be the primary driver of this phenomenon. This unexpected discovery opened a new era in cosmological research. Unlike ordinary matter, which decreases in density as space expands, dark energy maintains a constant or even increasing density as the universe grows. This has a peculiar consequence. As space expands, dark energy becomes more dominant, accelerating the expansion rate further. Dark energy does not directly interact with matter or radiation, but influences the very fabric of space itself. Rather than being an attractive force like gravity, dark energy acts as a repulsive force, driving space to stretch in all directions. Despite widespread acceptance, the nature of dark energy remains unsolved. Some scientists propose that dark energy may be a form of cosmological constant, a fixed energy proposed by Albert Einstein in his theory of general relativity, which he later dismissed as his greatest blunder. Another hypothesis suggests it could be linked to a dynamic quantum field that changes over time and space. The big question is whether dark energy is constant or will diminish over time. And if it fades, what will happen to the universe? These questions not only challenge current physical models, but also demand the development of new theories that transcend existing frameworks. The role of dark energy in the universe's expansion is undeniable. It not only shapes the universe's future, but also influences how large-scale structures like galaxies and galaxy clusters evolve over time. If dark energy continues accelerating expansion, the universe may face a scenario called the Big Freeze, where objects are stretched so far apart that no interactions remain, leaving a cold and empty cosmos. Conversely, if dark energy diminishes or reverses, the universe could collapse in a big crunch. Dark energy poses both a challenge and an inspiration for future generations of researchers. Missions like the Euclid and Roman space telescopes are expected to provide more data, shedding light on dark energy's role in the cosmos. These advancements may help answer major questions. What is dark energy, and where will it lead the universe in billions of years? Dark energy is not merely an abstract concept, but a key factor in shaping how we view the cosmos. Despite being mysterious, its powerful presence compels scientists to push beyond the boundaries of current knowledge to unravel the universe's greatest secrets. The universe's expansion is not only a physical phenomenon, but also brings profound consequences, reshaping how we perceive, observe, and understand the cosmos. From galaxies gradually vanishing from sight to the future isolation of large-scale structures, expansion raises many questions about the universe's long-term fate. One of the most striking effects of expansion is the increasing distance between galaxies. As expansion continues, light from some distant galaxies will never reach Earth, causing them to disappear from our observation. This phenomenon occurs not because galaxies are moving away, but because the space between them is expanding. In the far future, as expansion surpasses the speed of light, observers will only see a few galaxies in their nearest vicinity. The night sky will become progressively darker, and the universe as we know it will gradually shrink into a smaller observable realm. While galaxies within the local group, such as the Milky Way and Andromeda, remain gravitationally bound and may eventually merge into a giant galaxy, galaxies outside this group will continue to recede. The accelerating expansion will push these galaxies beyond the event horizon, where their light can no longer reach us. This will create an isolated universe, where each galaxy cluster exists as an island adrift in an empty void. This bleak future paints a picture of a cold cosmos, where intergalactic interactions become impossible. The unrelenting expansion of the universe also imposes significant limits on human observation and research. As galaxies disappear from view, future generations will lose direct access to the invaluable information we have today. The images and data collected by current telescopes like Hubble and JWST will become scientific treasures, preserving humanity's knowledge of the early universe. For future scientists, this presents not only an observational challenge, but also a reminder of the importance of preserving and transmitting scientific knowledge. As space continues to expand, the universe's expansion raises critical questions about the ultimate fate of everything within it. One common scenario is the heat death, where unending expansion leads to the complete dissipation of energy and interactions. Without usable energy, galaxies, stars, and planets will eventually fall into absolute stillness. Alternatively, some theories suggest the universe might reverse its expansion, culminating in a catastrophic collapse known as the Big Crunch. Whatever the outcome, the current expansion remains the pivotal factor shaping the universe's destiny. The expansion of the universe not only affects the distances between galaxies, but also shapes how we think about the nature of space and time. Each step in understanding expansion offers an opportunity to decode deeper mysteries about the cosmos's origins and fate. It challenges us to confront the limits of perception and drives the search for new tools and theories to continue exploration. The impact of cosmic expansion is not merely a distant observational phenomenon, but a complex story about how the universe's grand forces shape structures and guide humanity's future research. The expanding universe reminds us that everything changes, and that the knowledge we possess today may become all that remains in an increasingly distant and empty cosmos. The universe is vast and mysterious, but what will happen to it in the future? Will it continue to expand forever, collapse into a single point, or be completely torn apart? Scientific theories about the universe's future are not only captivating, but also lead us on a journey to explore the limits of human understanding. One of the most widely accepted scientific scenarios for predicting the universe's future is the concept of heat death. This describes a state where all physical activity in the universe ceases entirely, leaving behind a cold, empty, and motionless space. If the universe's expansion continues indefinitely, galaxies, stars, and planets will drift farther apart. This endless expansion reduces the density of matter and lowers the universe's temperature over time. Eventually, the temperature will approach absolute zero, minus 273.15 degrees Celsius, a threshold where no thermal energy can sustain physical processes. As a result, processes like star formation, nuclear reactions, and the movement of galaxies will completely stop. In this scenario, energy becomes evenly distributed across space, eliminating temperature differences between regions that could drive energy flows or sustain activity. This uniformity of energy leads the universe to its ultimate state of equilibrium, known as maximum entropy. According to the second law of thermodynamics, when entropy reaches its maximum, all physical systems cease functioning due to a lack of usable energy. The outcome is a dead universe, where all stars fade, massive black holes evaporate through Hawking radiation, and even fundamental particles cease interacting. Time in this universe becomes meaningless, as no events occur to measure it. This is what scientists call the heat death of the universe, where life, motion, and any signs of activity vanish. The idea of heat death, though cold and desolate, offers a profound insight into the nature of the universe. From an explosive, radiant, and vibrant state in its early days, the universe gradually transitions into infinite emptiness and silence. This scenario is not merely a scientific prediction, but also reflects the fragility of everything in the universe. It reminds us that no matter how brilliant, everything ultimately comes to an end. Although no one knows precisely when this will happen, current calculations suggest it could take hundreds of billions of years or more. This immense timescale surpasses human comprehension, but serves as a reminder of our small place in the grand cosmos. Studying heat death not only enhances our understanding of the universe's future, but also provokes philosophical questions about existence and the meaning of life in a universe destined for such an end. Heat death, with its cold and silent nature, paints a powerful picture of a universe that once exploded with energy and color, now returning to absolute stillness. It symbolizes the endless cycle of birth and death, emphasizing that even the greatest phenomena are but fleeting moments in the infinite flow of time. One of the most intriguing scenarios for the universe's fate is the concept of the Big Crunch, where the universe's expansion does not continue indefinitely, but reverses, leading to the contraction of all matter and energy into a single point. This scenario serves as both a reminder of the universe's fragility and a gateway to theories about potential rebirth and eternal cycles. According to this scenario, the universe's expansion may not be an infinite process. If dark energy, the factor driving the current expansion, weakens or gravity becomes stronger than expected, the expansion will slow, halt, and reverse. Galaxies, currently moving away from one another, would begin to draw closer. Gravity would cause galaxy clusters, stars, and planets to converge toward a central region. This compression would significantly raise the universe's temperature, creating a fiery environment that contrasts with the heat death predicted by other scientists. As contraction continues, the universe's collapse becomes inevitable. All matter and energy are compressed under immense gravitational force, converging at a singularity. This state mirrors the conditions of the universe just before the Big Bang, but in reverse. This phenomenon, known as the Big Crunch, marks a dramatic and violent end for the universe, where everything from tiny planets to supermassive black holes is absorbed into the singularity. However, this may not be the end of everything. Some scientists theorize that the Big Crunch could be the beginning of a new cycle. When the universe reaches the singularity state, the compressed energy might trigger another Big Bang, creating a new universe with a different process of expansion, evolution, and development. In this theory, the Big Crunch is not just a collapse, but a prelude to rebirth, suggesting a cyclical universe where every ending leads to a new beginning. The concept of the Big Crunch carries not only physical, but also philosophical significance. It raises questions about the nature of time and space, the meaning of beginnings and endings, and whether the universe truly follows an eternal cycle. If the Big Crunch were to happen, it would not only signify the collapse of matter and energy, but also the restructuring of everything, a complete transformation. Although this scenario remains theoretical and unproven, it remains one of the most compelling visions that modern science can imagine. The Big Crunch is not just a story of an ending, but a reminder that everything, no matter how vast and powerful, follows its own cycle. Stars, galaxies, and even the entire universe have their beginnings, growth, and eventual endings, or perhaps a rebirth to continue an endless journey. One of the most terrifying and mysterious scenarios for the universe's future is the Big Rip. This is when dark energy, the force currently driving the universe's expansion, surpasses all limits and completely breaks the fundamental bonds between the universe's components, leading to the destruction of all existing structures. Currently, dark energy is considered the key factor behind the universe's accelerating expansion. However, if dark energy becomes unstable and increases over time, it could overpower fundamental forces such as gravity, electromagnetism, and even the strong nuclear force. In this case, the universe's expansion would become uncontrollable. Objects in the universe, galaxies, galaxy clusters, stars, and planets would be pushed apart at an ever-increasing rate. The growing distances between objects would weaken gravity to the point where it could no longer hold them together. Once dark energy surpasses the threshold of control, it would cause the total destruction of the universe's structure. In this scenario, galaxies, once stable systems of billions of stars, would be torn apart into individual stars. Subsequently, even stars would lose their stability, disintegrating into atoms. More alarmingly, even atoms, the basic building blocks of matter, would cease to exist as dark energy breaks the bonds between nuclei and electrons. Ultimately, the universe would disintegrate into fundamental particles, drifting in a vast and disordered space. The final moments of the universe in the Big Rip scenario are described as a dramatic and unavoidable event if dark energy continues to grow. According to some theoretical calculations, this could occur within tens of billions of years. In the final seconds before the universe completely disintegrates, the expansion rate would increase to unimaginable levels. Everything, from large structures like galaxies to the smallest particles of matter, would be stretched and ultimately ripped apart, leaving behind an empty universe with no form or structure. The Big Rip is not just a frightening physical scenario, but also a reminder of the fragility of everything in the universe. From radiant stars to magnificent planets and sprawling galaxies, all could be destroyed by the very force that once enabled their formation and development. This is not just the end of the universe, but the complete disappearance of all forms of existence, leaving behind an infinite void of darkness and absolute silence. While this scenario remains hypothetical, it raises profound questions about the universe's fate and the meaning of existence. Is the universe truly dictated by dark energy, or are there unknown factors that could alter this trajectory? Whatever the answer, the Big Rip is one of the most powerful and haunting visions, evoking an image of a grand yet tragic end to the vast universe we inhabit. While scientists have proposed many theories about the universe's future, the ultimate answer remains an open question at the boundary between science and philosophy. The mysterious nature of dark energy, the key factor determining the universe's fate, is the missing piece of this vast puzzle, making all current predictions only relative. Dark energy, the force driving the universe's accelerating expansion, plays a central role in shaping future scenarios. However, our understanding of it remains limited. Will dark energy remain stable, grow stronger, or weaken over time? If stable, the universe might expand forever, leading to heat death. If it intensifies, the Big Rip could occur, with dark energy overpowering all other forces and destroying all matter. Conversely, if it weakens, the universe might become dominated by gravity, resulting in the Big Crunch. Each scenario, with its distinct possibilities and outcomes, reflects the complexity and unpredictability of the universe. Modern observational technology is crucial in the journey to decode the universe's fate. Advanced telescopes like James Webb and future projects are providing unprecedented data on the universe's expansion and dark energy. By studying light from distant galaxies, scientists can learn more about how dark energy has behaved in the past and present, and potentially predict its future. Advances in technology not only improve observational precision, but also open new questions, driving deeper understanding of the universe's origins and destiny. However, the question of the universe's future is not merely a scientific issue. It is intertwined with profound philosophical inquiries about the meaning of existence. Is the universe a random phenomenon with a clear end, or does it exist in an endless cycle of rebirth? Answering this question will not only help us understand the universe, but also ourselves, our role in an infinite space and unending time. Theories like the Big Crunch, Big Rip, or Heat Death are not just scientific predictions, but reminders of the fragility of everything in the universe, from planets and stars to massive galaxies. Whatever end awaits the universe, each scenario offers a compelling perspective on the wonder and mystery of space. It reminds us of the grandeur of the universe, where even the smallest particles contribute to a greater story. The journey to explore the universe's future is not only a scientific endeavor, but also a quest to understand ourselves, where science and philosophy converge to seek answers to the biggest questions. Where did the universe come from? And where is it going? While the final answer remains distant, this journey has brought humanity closer to understanding the origins and fate of everything in the vast cosmos.